the matrix elements with respect to some basis. Now suppose if you take a matrix A and I want the matrix elements with respect to some basis, suppose that basis is like EI, okay, and this is an orthonormal basis, so that EI sum over I, let's do the sum properly, sum over I is equals to the identity, so this is completeness. Now usually the matrix elements, so uh, matrix element of A is EI A E J, suppose A is an operator, is Aij. Now let me explain how this comes actually, why this is a matrix element. You can refer J.J. Sakurai, Quantum Mechanics, J.J. Sakurai, Modern Quantum Mechanics. Okay. Now the thing is, or you may not, you can have this in any book. A simple book is you can refer Jettili as well. I don't want to give any reference. So how this matrix comes? Okay, so matrix elements of A. So let me explain the mathematical structure. Now suppose you have a operator A, and the representation of operator A with respect to this basis EI. So that is why what I want to discuss. Achha. So let me write this completeness here. I, EI, EI is I. Okay, there's a sum over I, and you know that if I only take this, so this is the without the sum, so this is the projection operator, and EI EJ is delta Ij, so this is the orthonormal basis, and the above it is the completeness. Now if you multiply by two identity operators on the both side, you have the same thing on the left hand side, right? Now what I want is, I want to write this identity operator in terms of that basis. EI, okay, this is one and this is the other. Now remember, when you have a dummy index I, you can't have the same dummy index repeated, so you will not get the cross term, so you should take it like this, EJ. Clear? Now if I expand this, it looks like this, I J. Now if you expand this, I can take this sum outside here because this J has no involvement with I. So EI EJ is EI EI A EJ EI. Sorry, EJ. Okay. Now this part, what is this part? See, this is a scalar number. So if you can think that this is a bra, so this is a 1 cross n and in an n-dimensional space, and this is an operator, so this is an n cross n matrix, the representation in the n-dimensional space, and this is also a ket, so n cross 1, so everything gets contracted. So this is a 1 cross 1 number, so this is a number, so you can shift it in any position, okay, and what is left over is this outer product of this. So I'm writing it in a different way. I'm writing the two indices in one sum, I think you will not mind, and this I'm writing this in front, so EI A EJ times EI EJ. So that's the formula, and this is the A operator. Okay, this left side is carried. Now this is A ij. I am telling that this is the matrix element. Now how can I prove that this is the matrix element and what this thing is doing here? Okay, so what this thing is doing here. Now if this is the formula, let me expand it and let me explain this formula with a very simple basis. Let me take this basis on fundamental basis in R3. Suppose R3 if I take, so suppose E1 is 100, E2 is 010, E3 is 001, and if you take the transport of these things, so that's the bra, so E1 is 100, E2 is 10, you can take it in 2 dimension as well, so that will be most simple. Let's take it in, okay, leave it in 3. Since the board is short, I was stressing to give it in 2 dimension. Anyway, so this is the bra version of this. This is the K. Okay, and this is the basis I am taking, and what I want to do is I want to explain this formula, what exactly is happening. This is the matrix element, and what is this? What is this doing? Now let me take a particular term. I am erasing this part. So let me take a particular term. Suppose if I take A matrix, if I take a particular term, acha, how many terms are coming? Let me tell you how many terms are coming. So if let me expand this to sums in 2 sums. So if this is the thing, so I equals to 1 to 3, j equals to 1 to 3. That means the 9 terms are coming, right? 9 terms are coming. So 3 cross 3, 3 for I, 3 for j, and 9 terms are coming. And what I shall do is, let me take a particular term and explain it to you. Let me take a particular term. Suppose A12 I take. A12. If this is 1, 2, then this will be E. So then I is 1 and j is 2. I is 1 and j is 2. So what is this? So A12 is just a number. And what is this? This is a bra. So E1. So that says 100 times 2010 times A12. Okay. So equal to what I get over here by multiplying this. This is n cross 1, or rather 3 cross 1, right? So you have this. Sorry, I should have written it in the other way. I should have written like this. E1 is E1 ket, so that means 100. Sorry, and this is the E2 bra, so that is 010. Okay, fine. Now, what is this? What's the dimension of this? That is, this is 3 cross 1. So 3 rows and a single column. Here you have 3 columns and a single row. That means 1 cross 3. Now these two gets contracted and you get a 3 cross 3 matrix, right? So this is what? This is a 3 cross 3 matrix. And what's the value of that matrix? This A12 will be in front. Leave it. Now the matrix. First row into first column 0, 1, 0. First row into first column, first row into second column, first row into third column. So it get 0, 1, 0. Then 0 multiplied by all of these. So this thing. And this 0 multiplied by all of these is this thing. So that is 0, A, 1, 2, 0, 0, 0, 0 and 0, 0, 0. Now what's happening? If I take I equal to 1 and j equal to 2, in that term, in a particular term, this fellow gives you the matrix on which the A12 term will sit. See, 1, 2 term is sitting in the 1, 2 position. So this thing will identify which position the matrix element will sit. So that means this is definitely the matrix element. Okay, and for all the terms, for all the 9 terms, these matrix element will sit accordingly. So you have a sum of 9 matrices with a prefix as matrix element. So this is it. Thank you very much.